We've looked at solving systems of linear equations when there were two equations with two variables. We want to expand now to a system of linear equations. These are still linear equations because the exponent for every variable is 1. We have a system of linear equations with 3 variables. We have 3 equations. So what we're looking for now is what's called an ordered triple. We're looking for that single x, y, and z value that is a solution for each equation. It's an intersection point of the planes. An equation like that defines a plane, and we have the intersection point of planes. If it exists, doesn't always exist, as it was with the system of 2 equations and 2 unknowns. The lines could have been parallel, and if the lines were parallel, then we would have no intersection point, no common solution point for those equations. Well, the kind of equation that we can solve that we can get a single numeric answer is a linear equation in 1 variable. So our approach, when we have this system of linear equations in 3 variables, our approach will be to create a new system of linear equations in 2 variables. And then from that new system of linear equations in 2 variables, we can do just as we've done before. We can create a linear equation in 1 variable, and we can get the single numeric answer for that variable, work our way back to get the answers, the values for the other 2 variables. So what we want to do is we want to work with 2 of these equations at a time to eliminate one of the variables. And that will then create for us a linear equation in 2 variables. If we do that twice, we will have 2 linear equations in 2 variables, wanting to make sure that we eliminate the same variable both times so that we end up with the same 2 variables in those 2 equations. And then we can follow our normal procedure that we've looked at before to create our linear equation in 1 variable. Well, if I look at these equations, I notice that if I were to simply add these 2 equations together, wouldn't the z values disappear in the new equation that we would create? If I add equation 1 to equation 2, the z values already are additive opposites, and they will become 0. The coefficients will become 0, eliminating the z, which will simply create a new equation that only has x and y. So let's do that. If we add equation 1 to equation 2, x plus 2x gives me 3x, plus 2y minus 1y gives me plus y. The z terms cancel to 0, and 3 plus 3 is 6. And I have created a new linear equation in the 2 variables x and y. So I want to do that again and create another linear equation that just has the 2 variables x and y. Then I will work with those 2 to create my linear equation in 1 variable that will get me on my way to finding my ordered triple solution. Well, what if we take equation number 1? Let's call this equation 1, equation 2, equation 3. What if I take equation number 1 and multiply it by 2? Wouldn't that make the z coefficient negative 2z, which I could then add that newly created equation to equation 3? Because now I'll have additive opposites for the coefficients of z. So let's take equation 1 and multiply every term by 2. Don't forget to multiply the constant by that value of 2 as well. So we'll have 2x plus 4y minus 2z equals 6. And now I'm going to add that to equation 3, which is 3x minus 4y plus 2z equals negative 1. Oh, wow, that was nice. Not only will the z's cancel because I have additive opposites there, but I also have additive opposites for the coefficients of the y. So I have 2x plus 3x is 5x equals 5. I've created my linear equation in 1 variable that I wanted. Wow, that was nice. It doesn't always happen for us, but it did happen in this case. So we can now say x equals 1 when we divide both sides by 5. Well, now that we know x is 1, can't we take that value of x and put it into this equation, and then we'll be able to find what the y value is? So 3 times 1 plus y equals 6. So 3 plus y equals 6. So y equals 3. And we now know the x value is 1 and the y value is 3 in our solution to this system of equations. So let's take that x value being 1. Let's go back to equation 1 plus 2 times the y value, which was 3, minus z equals 3. So 1 plus 6 is 7 minus z equals 3. So if I subtract 7 from both sides, minus z equals negative 4, so z equals positive 4. And the ordered triple solution we have to this system is x is 1, y is 3, z is 4. Our approach then again was to get rid of the variable in one of the equations, to get rid of the variable in two of the equations to create a new equation that had only the same variables x and y. And unfortunately, while we were doing that, the y's disappeared along with the z's, in this instance actually giving us instantly our linear equation in one variable. And then we put that value back into the equations to determine what the y and the z were. So this is our first example of a linear equation, a system of linear equations where each equation has 3 variables.